So in the previous video, I talked about how studying more people might be a nice solution to uncovering more reliably what's happening within person, or at least within the average person. Maybe we can use it as prior information in clinical practice, or simply to study psychopathology in more detail. In this video, I'll talk about what this looks like to estimate a network model from datasets with multiple people. But to do that, I first need to explain some concepts on what are the differences between the data that you might have and the types of analysis that you might do. And this also comes to the second concern, or the second reason why you might want to estimate a network model from longitudinal data that I mentioned earlier. And that is that many people, they argue that cross-sectional data does not allow for studying within person dynamics, which is true. And that's because of that, we should not do cross-sectional data analysis, and we should always study between person effects, because we are psychologists and we're interested in what's happening within the person. And that argument I have a bit more trouble with, but I'll explain that in this video. So to start, I want to give a bit of an overview about if you have more observations and more people, what type of data you might encounter. And following that, I want to talk about what type of analysis you can then do, which are linked in a way to the type of data you have, but not necessarily the case. So here I represent a space of potential observations that you might have. So we have people measured potentially at different time points. So this is a red person, blue person, the purple person, the green person, orange person, and they could be measured at different time points. So maybe every day we could have measured someone, and you might get different results if you measure something today or tomorrow or the day after. One type of data that you have seen before by now is single measurement data, which means that we only have data of each person once at one particular time point. So this is usually called cross-sectional data, because it is a cross-section of this cube, or this square here. Right, you see this, like we cut it here, and that's only the data that we have. That's why it's called cross-sectional data, but I don't really like to use that term, because it's very confusing to cross-sectional analysis, which I'll talk about in a bit. Simply having this type of data means that you have only one measurement per person. But it could be that that measure is not a certain point in time, but rather an average or over a long time, or maybe a stable average. So maybe this is place of birth. Whatever you do in life, your place of birth will not change. Right? You'll always be born in one place. Or maybe it's if you experience a certain amount of depressive thought over a period of 3 months, for example. Is it really a point of time, or is it just one measure, right? Or maybe it's a clinician-rated effect, things like that. So that's why I like to use the term single measurement data here. Another type of data that we might have is n=1 time series. So this is the type of data I talked about in the previous video, where we have many observations of one person. We can use this to look at this person over time. Then a third type of data is panel data, where we have a few observations of many people. So here we have many people measured a few times. And we can also think about n=1 time series, where we have typically less people, but measured more intensely. Maybe in panel data, we have 3, 4, 5 measures of maybe 1,000 people, or 5,000 people, or 500, but like a lot. And it's more than one time series, we might have like 50, 60 observations, or at least more than 20 of usually less people, maybe like 100 or so, because it's very hard to get this type of intensive time series data. yeah, if you have, and of course there's a gray area between panel data and time series data, but I won't talk about it now. So depending on what data we have, we can do different types of analysis as well. So I'll talk about that now. So here we have again our window, our time, time by people overview of the world. Then a cross-sectional analysis is a statistic that we compute over people at a fixed measurement occasion. So for example, we can compute a correlation or a mean or a variance or any statistic that you might encounter in a certain sample. And we can choose to do that over the population at a fixed measurement occasion. And that can be some value, like 0.5 or so. This is just a random number I came up with. This is often called a between-person analysis because we are looking only between people, because we only have one observation per person, so we're looking at individual differences. But that's not technically correct. So a sectional analysis like this really would be an analysis on a dataset that is just one observation in time where there could have been other observations as well at other time points. True between-person effects relate to effects that are between things that are stable across people. So for a true between-person effect, we would collapse over this time dimension, and we still have only one observation per person. But these observations, they wouldn't be different at another time point. They relate to something that is a genuine between-person or individual differences or a stable effect. So for example, correlations between stable averages on how my average stress relates to my average anxiety. That's different than the correlation between stress and anxiety at a certain time point, right? That's different than how I am the correlation between my average levels of stress and anxiety. That's important to distinguish because this, it tells something different. I'll show some examples later, where this is different. Then another type of analysis that we can do is a within-person analysis, and then we look at the effect of one particular person over time. And this is where the term within-person comes from. It means within the data of a person. So within the data of a person, we might be able to establish something. So that means we take one person, there might be others, and they might have different effects, and we look at them, at that one person over time, and then we establish some statistic in that one person over time. So for example, we correlate stress and anxiety. Stress now means the deviation on stress from the person-wide mean, because we can't look at the average of this person. So maybe this person is on average very stressed, on average very anxious. That we can't do much with because we don't have statistics to deal with there. We just have like one average. We can't relate it to anything else. That's why we can only look at the deviation from this average. So again, this correlation might be something different. This correlation tells me that if this person 4, not person 3 or 2 or 1, but person 4, experience more stress than their average on a certain day, then that person tends to also experience a bit more anxiety on that day than their average. Whereas between-person correlation tells me that a person that on average experiences a lot of stress might also on average experience a lot of anxiety. Those are two very different things. Now finally, we have fixed effects, which you might hear if you do multi-level modeling. And what we do in fixed effects, we aggregate over people. So we basically create one non-existing average person, and then we look at what is happening within this average person. So we try to establish a correlation within this average person, which gives us something that we can use to generalize to people. But at the same time, it gives us a relationship that is not actually based on the data of any particular person in our sample, because this person did not exist. See? We had person 1 to 5 here, not this non-existing average person. So we might get a correlation there, but it's not actually a within person effect. Now this is confusing because actually many things here are confusing. Many people will call this a between person effect, this cross-sectional relationship, but it actually isn't. And many people will call this a within person effect, this fixed effect structure, but it actually isn't because it's not based on the data of one particular person. Very confusing. And yeah, I think it's just good to think a bit about what this means. Now this is the main argument that you might see if you read into this literature on cross-sectional modeling versus longitudinal modeling. Not only on networks, but the argument is made a lot in network analysis, but it's equally valid for example, fact analysis. That is that all these things give some different results, right? There's only one time when that's not the case. And that is if a system is called ergodic. Ergodic is something from physics, but it basically means that every person in my sample is an exact replication of each other. This means that every person is the same. If every person is the same, with the same averages and the same relationships between variables, then and only then will my single measurement analysis, my cross-sectional analysis based on a single observation, for example, a score from today, only then will that correlation equal the within person effect. So if this is the case, every person is exactly the same, with the same means and the same relationships, then if I would study one person, I would get the same results as if I study another person, if I aggregate over people, or if I do a cross-sectional sample. It also means that there are no between subject differences, because people don't differ, so there are also no relationships between stable averages. This is not true. This assumption never holds, because people differ in psychology, and we know people differ. The whole fundamental foundation of psychometrics is based on the idea that people differ. So this, we know, is not true. And that means that we cannot take a cross-sectional effect, so let's say this correlation 0.5, and generalize that to the within person level with this one, this one. Yeah, and which is mainly the argument. So many people say, okay, we are interested in within person effects because we're interested in what happened within the person. Now, I think that a within person effect relates to something that's happening within the data of a person, not within the person itself. And then people say, okay, cross-sectional finding cannot, or between subject effects cannot relate to that, so we should not look at that, we should only look at time series effects. This argument you'll see sometimes. And yeah, it is true, that's the case. But I think the main way out of this is not so much not to do cross-sectional analysis, but more to keep this in mind that this is the case, that these effects are different and that you might find different effects on different levels. And it's also worthwhile to separate these within and between subject effects from each other because they can be very insightful. So to give an example, here I have two networks, partial correlations, but let's say it's only two variables, so they're correlations. You have a positive effect here and a negative effect here. So if you have only one sample, cross-sectional data set, we cannot separate within and between subject effects. That means that we cannot see if two variables are correlated because their averages are correlated. People on average that have one variable high tend to have another variable high, or because deviations from that average in one particular day were correlated. If you have more than one observation or more than two observations per person, we can separate these effects and we can look at them both. And they might tell you a different story. So for example here, I have an example where I collect a data set on spelling errors and typing speed. So let's say I let people write a text participants, I see, okay, how fast did you write the text? How many spelling errors did you make? And I do this many times, like every day, for example, for a series of, I don't know, like several weeks or so. If you do that, we might find this. We might find a positive relationship at the within-person level, and the negative relationship at the between-person level. Now, at this point, maybe you want to pause the video and think a bit about what this means. Okay, so I hope you all paused the video and thought well what this means and why this might be the case. So what does this mean, a positive within-person effect? This means that whenever a person is typing faster than their average, that person makes more spelling errors faster than their average. More spelling errors than their average. This makes sense, right? So if I'm typing faster than I normally do, I tend to make more errors. The between subject effects means that a person who average types fast, on average makes fewer spelling errors. Now, does that make sense? I think it does, because people that on average type fast, they might be really good at typing, right? They might be professional writers, or the people in the courtroom that make notes. They have to do it every day, do a really good job there, and not make any spelling errors. And you might have people that are not experienced writers, and they just take very long time to write. And because of that, because they're not experienced writers, they might also make more spelling errors. But this makes sense, right? It might make sense that you get different results at different levels. And some would call this paradoxical. It's not really paradoxical, because you can explain this. Now, in this case, if you want to think in terms of causation, we can look at both networks, right? So, okay, if I want to reduce the number of spelling errors that I make for my next text, then I should type slower. So I should look at this within subject level. But this between subject level can also be illuminating. You can tell me, okay, like if I actually want to become a person that doesn't make a lot of errors, and maybe I should practice writing a lot. Different conclusion. Now here I have a different example, and the only thing that's different is the notes. So the relationships are the same, I just change the notes. Heart rate, physical activity. So this means whenever a person has a higher heart rate, let's say a person has a higher physical activity than their average, then the heart rate is higher. Makes sense. If you start exercising, your heart rate goes up. This means that a person that on average is very physically active, on average has a low heart rate. This also makes sense, because people that are very active and run all the time, they tend to have much better heart rhythm. Right? Now, if you're a medical doctor and someone comes to you and you are concerned about their heart rate, what would you do? Let's say we take his data. We wouldn't say, okay, let's only look at the within subject level, because we know we need to look within people, so we don't care about the within subject level. So we only look at the within person level, and then based on this, I recommend that you never exercise again, because your heart rate goes up when you exercise. That's not what you would recommend, right? You would recommend, okay, you need to become more physically active, because we see in the data that it actually helps with reducing your heart rate on average. So now suddenly we would look at the between subject level. Then the point I just want to make here is that both of these are interesting to look at. So it's not really true that you should only look at one level. It's nice to look at both. Then there's another thing that we can consider, and that is the time frame of our study. So here I have an example where I just generated some pseudo data. It's not actually real. So the red blocks means here that the person experiences stress. A blue block means the person experiences anxiety. So let's say this person is stressed and not stressed and stressed and not stressed and stressed, etc. And I put these blocks kind of close by each other. I even put anxiety a little bit after stress starts. And if we now study, let's do a time series study of a person, or like a multi-level time series study for a few months in this period, we might be able to establish a within-person relationship between these variables, because we have enough variance, enough covariance to establish that. But if you have something like this, like suppose, well, we don't really have to suppose that, but if you have something like this and you have one person that we measure, that's only one person. You have only one person that we measure over time, and yeah, that person is healthy and is smoking. And that doesn't change because the person doesn't stop smoking. There's no variance. We can't uncover anything here, right? So this time series study is not going to uncover anything. We don't have enough information. We just have here yes, here no. So the only thing we can do now is look at the between subject level and look at multiple people and see, okay, so compare people at this time where there's no variance. Compare the relationship between these variables at the between person level. But that doesn't necessarily mean that any relationship we uncover here is not happening within people or is not causal. The relationship between smoking and cancer has been uncovered using between person designs, right? By comparing people that smoke to people that did not smoke, for example. And if we do want to uncover this in a within person setting, then we have to think about longer time frames, right? So then we want to do maybe a panel study that covers multiple years and not measure people like 5 times per day, right? Because you're not going to measure someone 5 times per day asking, are you still a smoker? Are you still a smoker? Are you still a smoker? But if you measure every year on a period of 10 years, then we might find a within person relationship. And that means that it's not as clear cut as what I show here. It could be that a between person effect of one time frame becomes a within person effect at a longer time frame. And so again, what this means is that it's interesting to look at this between person level and to look at what it can imply. And that it can also lead to valid within person inferences on things that are just slower. Now, a last thing that makes it even more complicated than we already did before, but I already talked about this earlier, is that we also have to take into account that there are some temporal dynamics. So there's 9 o'clock and 1 o'clock and 5 o'clock, and there are effects between these consecutive time points that we might also want to uncover, because we might want to see what happens over time. Now, it could be that we, again, find something different between these two models. So we can, as I said before, using time series data, we can separate temporal networks from contemporaneous networks. And we might find different effects there. So for example, we might find something like this. Whenever a person is exercising, 3 hours later, that person is less energetic. But while the person is exercising, that person is more energetic. Does that make sense? Well, yes. I mean, while you're exercising, you're more energetic, right? Because you're exercising. Or maybe you started exercising because you're energetic. Or maybe you get energetic from exercising. Right? But 3 hours after exercising, you might be really tired. Right? You might be like, okay, I've been running around for 2 hours. Now I'm just crashing on the couch watching Netflix. But this might make a lot of sense. Not paradoxical. And it's interesting to also split the effects between these contemporaneous and temporal effects, because both might tell you a useful story. So that's what we can do with, and it's more than one time series data, we can actually separate all these things. And we no longer get one network. We no longer even get 2 networks. We get 3 networks. We get 3 networks that we can look at. A temporal network, and we can get one per person even. Contemporaneous network, so this is for the average person, with fixed effects, but we can also get one per person. And a between subject networks. And all these things can be useful, and they can also tell me something different. Right, so for example here, this actually I found it interesting because this was just a random idea I had, a hypothetical network, but in the data I actually found this relationship exactly like that. So exercise led to being less energetic 3 hours later and being less outgoing 3 hours later. But while the person was exercising, that person was more energetic. And at the between person level here, this means that a person that's on average exercising a lot, on average is more adventurous, which I thought was interesting. Here we also see similar effects. So, for example, we see that finding it difficult to relax on average leads to people being more irritable 3 hours later or the next time point. And also related to these two variables related to each other at a contemporaneous level, but not at the between subject level. So here, a person that's on average finds it difficult to relax on average was not more irritable, or at least we did not uncover that. Might be a lack of power, of course, as well. Here's also something interesting happening because there's a negative effect here at the between subject level, but a mildly positive effect at the contemporaneous level. Could be that this is a causal collider effect, or a common effect here, where difficult to relax causes worrying and hopeless causes worrying. So being a person that is hopeless on average, feels hopeless on average, might lead to being a person that worries a lot on average. And being a person that has a lot of difficulty to relax on average might also lead to being a person that worries a lot on average. I think might make sense. And it's just to show that you can get some different results at all these levels, and they're all interesting to look at. Now, I won't talk about the code to do this. It's not that hard, but there are considerations to be made. So if you're interested in the code, then Adela's textbook has nice examples of that. Chapter 9 and Chapter 10, especially Chapter 9, includes a lot of information that I talked about in this video as well. Chapter 10 will include a lot of the examples of the code that you can use for this. All right, that's it for this video. And then in the next and final video, I'll give 2 examples of networks estimated from longitudinal data.